Hello students, welcome. In this video, we will be discussing digital electronics in general and positive and negative logic in particular. In fact, throughout this course, we will be dealing with only positive logic. But this video deals with both positive and negative logic only to understand what is negative logic and to differentiate between positive and negative logic. Before discussing positive and negative logic, let us see the general picture. In digital systems like computers, mobiles, or any other digital device for that matter, data is being processed, stored, and even transmitted in the form of digits, zeros and ones. We human beings can differentiate what is zero, what is one. But how does a computer or any other digital device differentiate or recognize 0 as 0 and 1 as 1? For example, on CD-ROMs, data is being stored on the surface of the CD-ROM as bits and LANs. When data is being stored on the CD-ROM, in our language, writing the CD, laser beam is being used to create pits on the surface of the CD-ROM to represent 0. And where pits are not created, it is LANs to represent the ones. And that's how data is being stored in the form of zeros and ones in the form of pits and LANs on the surface of the CD-ROMs. But when it comes to hard disk, which is a magnetic device, we know hard disk drive have got platers inside, which are shiny circular objects which are magnetic in character. And these platers are divided into billions of tiny spots in terms of tracks and sectors. And each tiny spot can be either magnetized or demagnetized. When it is magnetized, it represents 1. When it is demagnetized, it represents 0. So, zeros and ones can be represented on hard disk drive when it is magnetized or demagnetized. Now, when it comes to transistor or computer memory, zeros and ones are represented with the help of voltages, electric voltages. Say for example, 0 voltage is used to represent logic bit 0, and say for example 5 voltages are used to represent logic bit 1. So the point is, data or zeros and ones can be represented in various ways using different methods depending on the object or the medium on which data is being processed or stored or transmitted. In other words, zeros and ones are represented sometimes mechanically, sometimes magnetically, and some other times electrically. Now coming back to our discussion on positive and negative logic. Think of what happened in the transistor, where bits were represented with the help of electricity. In the case of positive logic, a low voltage is being represented by logic bit 0, and a high voltage is represented by logic bit 1. Say for example, we have two voltages where 0 voltage and plus 5 voltage. Definitely one is low, the other one is high. So the low voltage is being represented by 0, where 0 voltage will be represented by logic bit 0, and plus 5 voltage will be represented by logic bit 1 in the case of positive logic. And if the voltages are minus 5 and plus 5 voltages, where minus 5 voltage will be represented by logic bit 0 and plus 5 logic bit will be represented by logic bit 1. It is the other way around in the case of negative logic, where a low voltage is represented by logic bit 1 and a high voltage is represented by logic bit 0. Again, the same example, we have 0 voltage and plus 5 voltage. So what will 0 voltage will represent? Definitely it will be logic bit 1, and plus 5 voltage will represent logic bit 0 because it is negative logic. And if the voltages are minus 5 voltage and plus 5 voltages, of course minus 5 voltage will represent 1 and plus 5 voltage will represent logic bit 0 because it is negative logic. We said during this course we will be dealing with only positive logic. But what are the situations, or can there be any situation when negative logic can be used? Now think of a light-based motion detector where a beam of light or the laser beam is being transmitted from one corner to the other, where the transmission of light can be assumed at high since there is no obstruction, and this can be assumed to be at logic state 0. The moment somebody or something moves across, obstructing the light, when the light goes low, the logic bit is set to 1, indicating a movement. So this is a typical example. When the light is high, the bit is set to 0. When the light is low, the bit is set to 1. This can be an instance of negative logic, though not a perfect example. Now it's time we look at the truth tables. We look at the truth table of OR gate only for both positive and negative logic. Now this is the truth table of OR gate, where we have 2 inputs and 1 output. When the inputs are low, both A and B are low, then the output is low. For all other cases, the output is happen to be high. Here you see the truth table of OR gate for positive logic, where 0 stands for the low and 1 stands for high. So naturally the first output is 0 because in the OR gate we have the output as low, and for all other cases we have output as 1 since the output is high for all the other 3 cases. Now this is for positive logic. Now we consider for negative logic, we have the same table on the left, that is truth table for OR gate. Now what happens when it is negative logic, where 1 stands for low in the case of negative logic and 0 stands for high in the case of negative logic. Now you can see the changes accordingly for the truth table of OR gate in the case of negative logic. The first row gives the output as 1, which stands for low because inputs are low and low, 1 and 1. So the output is 1. All other cases we know the output is high. So 0 represents high. And now finally, for the positive and negative logic, an OR gate in the positive logic system becomes an AND gate in a negative logic system. So you can see the equivalences here in this table. So an OR gate in the positive logic system becomes an AND gate in the negative logic system. Similarly for all other cases, so the equivalences are given over here. With that, we conclude our discussion on positive and negative logic. Thanks for watching. Bye.